Hi, I am Analúcia Schliemann, and I welcome you to our session, and I am grateful to NCES for including us in this summit. I will be joined by David Carraher and Montserrat Teixidori in presenting the work we did within the Poincaré Institute for Mathematics Education that is offered by Tufts University and was developed through a grant from the National Science Foundation to Tufts and PreK. The Poincaré Institute for Mathematics Education developed a teacher development program. It was a joint work from mathematics education researchers, research mathematicians, physicists, and school districts. It was offered online with monthly face-to-face meeting and uses functions to integrate topics across the K-12 curriculum. For decades, we have witnessed that state assessments and NAEP results show no significant reduction of difference across ethnic groups. However, our previous longitudinal intervention studies from grades 3 to 5 in multi-ethnic districts of low-income families have shown minority students' capabilities as they were introduced to algebra and functions, concepts and representations. In fact, this was done at a time when the NCTM and mathematics standards and frameworks were calling for algebra and functions throughout the K-12 curriculum. But how would teachers address this goal? Were they ready to do it? Our answer to the question of how teachers could face those goals was to create this long-term teacher development program. It aimed at interconnections of mathematical topics within and across the grades through functions and their representations. It aimed at the integration of mathematics and pedagogical content. Interaction among teachers and between teachers and instructors was key for the program. Teachers' analysis of videotaped classroom activities and of student works from research or from previous cohorts were part of their assignments and activities. They interviewed the students, and from there, they planned, implemented, and discussed their own lessons. Students' conceptual understanding and representations were guided to emerge from their analysis of relationships between sets of physical quantities instead of computation on specific values. Considering equations as the comparison between two functions have been one of the goals of the project, both for equations and inequations.
Hi, I'm David Carraher, a retired senior scientist from PreK in Cambridge, Massachusetts, and I'd like to go into some of the expectations that teachers might have and teachers' mathematical knowledge and their expectations about students, and I'll focus on functions. Now, it's interesting, when one talks about functions to teachers in grades, for example, 3 to 8, many of them will say, well, I don't teach about that, because actually in the Common Core, functions it says here grade 7, but they really only come up formally in grade 8. And strangely, equations and expressions are highlighted in grades 6 to 8. And we at the Poincaré Institute have been taking a slightly different stance that requires a little explanation, and that is that functions can and should be present in the curriculum early on, and that means as soon as operations are being taught, one can talk about things like averages or tendencies to increase or decrease and so forth. In other words, one could start thinking about sets of data or sets of numbers, and that automatically brings you into the realm of functions. Okay, so operations, as soon as one talks about operations in the context of sets of numbers or sets of quantities, one is talking about functions. So when we say functions have a role in the earlier grades, we don't mean that teachers should be talking about bijections and injections and so forth. Functions can continue to be formally introduced in grade 8, but they have a real role to play early on because we want students and teachers to be thinking about variables. Okay, and some of the ways in which functions can be represented are through natural language, first with relations among physical and geometric quantities, and next using tables, linear graphs, and even algebraic expressions. And that might seem a little bit strange to people who think of algebra as something that comes very late. But I'll show you some of the tasks that we used with the teachers and also with the students from grades 3 to 6 in the early algebra project. And I think they may surprise you, as they have surprised many of our teachers, that kids are able to work with functions and work with algebraic notation much earlier than was originally thought. So the first task I just want to go over quickly is what we call the candy boxes problem. And we would give this kind of a problem to third graders, right off the bat. A teacher comes into the classroom with an actual box of candies. Well, it's impossible to see how many are in there, but he says or she says to the students that one student, say John, has a box of candies and an extra one on top. And Maria has a box of candies and 3 extra candies on top. What can you tell us about the relationship between the amounts that they have? And it turns out that most kids see this as a problem of guessing the number that are in the box and then just adding the additional candies to it. And that's fine. But when they start putting their estimates into a table and look at all the estimates on the board, they begin to realize that all of these possibilities, for example, the numbers 10 for John and 12 for Maria, that works, but so does 20 for John and 22 for Maria, and so on and so forth. But although we don't know how many candies are in the box, it could not be the case that John has 11 candies and Maria also has 11 candies, okay? Because it has to be the case that Maria has 2 candies more than John. So this is a kind of problem that involves simple functions of n+1 and n maps to n+3. And kids are able to understand this. They originally think of it in terms of specific values, but they eventually see that they can talk about these sets of values. And so we believe that we're introducing them to variables early on and even to notation for standing for variables. Now, a little bit later on, in grade 3 or even in grade 4, we introduce a problem we call the wallet problem. It's the following. Mike has some money in his wallet and he has $8 in his hand. Robin has 3 times as much money as Mike has in his wallet. What can you say about the amounts of money that the students have? Do you have a hunch about who has more money? And in grades 3 and 4, first of all, it's not clear at all what's really being said, and one has to spend a lot of time trying to get them to see what's really being said. Some people, for example, some students will claim that Robin has 3 times as much money as Mike does, and that's not quite the case. It's 3 times as much money as Mike has in his wallet. Give me a little break here. Oh, okay. I should mention that this problem, as the other problem before, the teachers in the Poincaré Institute see videos of 3rd graders and 4th graders approaching these problems in the classroom, and they also try out variants of these problems in their own classrooms. They videotape them, and they report on them and analyze the results. So this is a learning experience in a couple of ways. They see what took place in the early mathematics classrooms, and they try them out in their own variants of these problems. Now, here's a typical answer, for example, that children might have when they're asked to think about the different possibilities for the wallet problem. You'll see this student made two columns. Was talking about Mike and Robin in this case, and has for Robin, if Mike has 0 in the wallet, he has 8 plus 0, and Robin has 3 times 0, he has nothing, and so on and so forth. So this table shows the various possibilities that could occur. And it's usually only when students come to the point where they're looking across this range of possibilities that they realize that you can't tell necessarily who's going to have more candy, Mike or Robin in this case, because it depends on how much money is in the wallet. Here's another representation given by a 3rd grader. Mike has $8 in his hand plus more money in his wallet, and he uses an actual wallet icon with an N to represent part of his money, and then he shows $8 with a bill underneath, and he writes N plus 8 is whatever that total is for Mike. And Robin has N times 3 money. So here we have a child representing variables and actually using algebraic notation to capture the functions. The functions are N plus 8 and 3 times N. Oh, we actually get to the point, usually in 4th grade, that they're asked to interpret this sort of a situation where you have linear graphs of Mike's amounts and Robin's amounts. And we find in the course of an hour of discussion, the students in 4th grade who have been used to these sorts of activities will readily come to the conclusion that that point in the middle of the graph, point 412, which shows that when $4 in the wallet, they each have $12. That's where the two function lines, the graphs of the linear functions, intersect. And that's actually the solution to an equation. So you see, this shows how an equation can be represented as a comparison between two functions. And here we have the solution, which is 412, but we also have the right-hand side in which Robin has more than Mike, and the left-hand side of the display in which Robin has less money than Mike. And these are kinds of activities that one would normally associate with 8th, 9th grade, but we found that 4th grade children, even in a disadvantaged neighborhood and from various ethnic backgrounds, they can handle this sort of thing if they're given the opportunity to talk about the results and if the teacher is aware of how to exploit this as a problem. So it turns out that this sort of a problem is very beneficial for our teachers. Finally, I'd like to just mention another problem, which is also one that we studied in 4th grade. The problem involves candies that are in tubes, those rectangular containers, boxes, and in a bag, the bag presumably being transparent. So George has 3 tubes of candies, he has a box of candies, and he has 6 loose candies. And Lucy has 1 tube of candies, 1 box of candies, and she has 20 loose candies. Now, only after they've really made sure that they understand that there are the same amounts in each tube, there are the same amounts in each box, we then tell them that they happen to have the same amount. And so they reason out about how many there are going to be in actually not in the Y, but in the X. They will solve for X. And they will use partly their iconic representations and partly the algebraic representations. So this has expanded our notions of what we can expect from students in early grades, but it also, we hope, opens up teachers' minds about the kinds of activities that they could envision trying out with their students.
Hello, my name is Montserrat from the Math department at Tufts University, and I am going to talk a little bit about the courses in the Poincaré Institute. We already mentioned that there were 3 different courses that I am going to discuss in a moment, and we provided the teachers with an extensive collection of notes on mathematics and pedagogy integrated together. We had video lectures, mostly for the mathematical part, because we found that that helped the teachers follow it better. They had problems that they had to solve and discuss. There were software demonstrations that they were examining either on their own or with the students. And they had, very importantly, videos of prior classrooms implementations. We even used some of the first, second, third cohort in the following third, fourth, fifth cohort, so that the teachers could see what had happened before. All right, I am going to talk a little bit about the course structure. Each course had 4 units and the final project. The first 2 weeks of each unit was an integration, so it was more the learning part, the integration of the mathematical and pedagogical content, where the teachers were in groups, in online groups mostly, of different schools and different districts even. And they were reading the notes, trying to understand and make sense of them. And then they were working on problems that we gave them and discussing them with the help of a mentor that was participating online. The third week was very different. So in the third week, they met in small groups in schools, and they were supposed to either interview the students or implement some small activity in their classroom. So it was completely hands-on. But the activity had to be related to the things they had been learning in the 2 weeks. So whatever they had learned in the 2 weeks didn't stay in the abstract. It had to be going down into their classroom right away. And there was also a final project, which was an extra 3 weeks. They had to write a proposal. The proposal was reviewed and received feedback from mentors and from their peers in the small group. And then they had to implement it and finally discuss it and say what they would do next time to make it better, so that everything could be improved. So hopefully that had an impact on their classes right away. For the content of the courses, the first course we started with numbers, because that was what the teachers wanted. They wanted to have a discussion of fractions, for example, and we presented all the usual representations of fractions, but we also presented some extra ones. So in addition to having a number line and having the pie charts and all that, a fraction was also represented by a linear function in the plane, and we are going to see it in an example in a moment. Then we try to relate numbers to functions. We introduce functions for those who were not very familiar with them, and we introduced the mathematical idea of function, but we also introduce it mostly from, here is the situation, how do we relate this with a function? And in the early grades, it could be just simply making a table. In the more advanced grades, you would come with the algebraic expression, and in between, plenty of different representations of the functions, be it with arrows on a single line, with arrows between 2 lines, a graph in the plane. So there was a lot of hands-on and representation. The second course was trying to solve equations. And as David pointed out, when you think of an equation, we think of 2 functions. When do they take the same value? Or even more interesting, when do they have one less than the other or one above the other? So not just equalities, but also inequalities. And we want to know how to solve that. The usual thing is, once you have the situation, you write the equation, and now forget about the situation, forget about everything that has brought you there, and now do algebraic manipulations. But we wanted to do it a little bit differently, to be more engaging and to be more able to understand the process. So we explain the solution of equations as applying transformations, not just to the equation itself, but to the whole plane where that equation was represented. And not every transformation is going to preserve the solutions, but some will. And that's what we explain. And we have to say there were many levels of teachers in the program. The early grade teachers often deal with situations that make sense only for integers. So we talk a little bit about Diophantine equations. For example, you are trying to figure out the number of televisions that you can buy, right? You cannot buy 0.3. And we also talk about polynomials and factorization because that appears later. And that allows us to compare the properties in terms of product properties of integers with the multiplication properties of polynomials, which are very, very similar. To put the two structures one next to the other, for a mathematician, that's a very natural thing to do. For teachers, that were two completely different worlds, but we show them how you relate them and how you understand one and the other. And of course, at all times, we were trying to think about modeling things. And the third course might look a little bit advanced, but actually it's not so much. We were trying to talk about change and invariance. So rate of change, when it is constant, that gives us linear functions, and it's related to ratio and proportion. And when it's variable, it's other types of functions. And we can even think of the rate of change and which situations correspond to a linear function, which situations correspond to a nonlinear functions. For example, you are filling a certain jar with water, and depending on the size of the shape of the jar, it's going to be giving the height is going to be a linear function, or it's going to be a very different function. That was one of the examples that we proposed. Let me give you some concrete examples of things we did. And the example that I want to mention is fractions. We were representing fractions with, of course, verbal descriptions and all the usual things, but we were also representing fractions with lines in the plane and the slope of a line. And you can see here in my picture two different lines. One corresponds to 3/2, which has a positive slope, and one corresponds to negative 1/3, which has negative slope. And you can see a way of representing the different representations of the fractions. So 3/2 is the same as 6/4, and so on. Each one of these possible fractions corresponds to one of these red dots. When you intersect the line with the grid formed by the integers, you get a certain fraction. The first number is the denominator, the second number is the numerator, so that corresponds to the slope of the line. But we can do more. We can also represent the number itself. You see that blue vertical line? That is the line x equals 1. When you intersect the red line with the blue line, the point on the blue line of intersection corresponds to the 3/2 that gives us the slope of the line. So that's the way to relate the line to the number. It also allows us to understand why, when you divide two negative numbers, you get the number 3/2, which is positive, because the numbers on the third quadrant correspond to two negatives, a numerator which is negative and a denominator which is negative. But the quotient, the slope, is still a positive number. That's something that kids have a problem understanding, the rules of the product and quotient of numbers for the signs. It's usually difficult to explain. That's a way to figure it out. And same thing with the negative slope. Here you have one of the numbers is positive, while the other is negative, and the quotient is always negative, right? But you can change which one is positive and which one is negative. It also allows you to order the fractions, because when you take the point of intersection with the blue line, the ones that come on top are the bigger, and the ones that come towards the bottom are the smaller. So that's a way to understand things. There are other uses of fractions. For example, we presented some algebraic problems that were introduced with just a story about some children sharing bits, and the fact that when you share bits in two different groups, you end up with the kids having the same number of bits in each of them. It's giving you a relation that if A over B equals C over D, then A plus C over B plus D is also A over B. So that's the algebraic representation of an everyday situation. Most of the teachers were dealing with the numbers first, and some of them tried with the algebraic expression and understood that all these properties they teach about cross multiplication of two fractions which are the same, give you the same, allows you to work algebraically and understand some kind of miracles that happen in math that sometimes people don't know how to explain, but it's not so difficult to explain once you use algebra. Algebra is a useful tool, and we wanted to convince the teacher that it's a useful tool and they should explain it to their students that way. And finally, my last example is about functions. David already gave you some very nice examples, but that's another example in which we were comparing the position of a truck with the position which goes at 40 miles an hour and lives 15 miles down the road with the car which is going faster at 60 miles an hour, and you want to know when the car catches up with the truck, right? And you would write the equation 60x equals 40x plus 50. Now, as I explained before, we don't just stop here, and now when you have the 60x is 40x plus 50, now go to algebra, forget about everything else. We can think of solving the equation in terms of movements in the plane. You want to preserve the solution. In order to preserve the solution, you have to consider transformations of the plane that keep the point of intersection on the same x value. So you can move the points up and down, but you cannot move the points left to right. You are going to change the y value, but you are not going to change the x value. That gives you the solution. First, when you subtract from both sides the 50, you get the green lines. And that can be interpreted also in terms of what is going on. The 20x equals 50 is the difference between the two speeds is 20x. So that's how fast the car is going with respect to the truck. And 50 is the distance they have at the start that they need to catch up. So at 20 miles per hour, how long will it take you to cover these 50 miles? And when you do the division of the two things, there are two little lines here that I cannot blow that up, but if you blow the screen up a little bit, you'll see the two little lines at the bottom, and they still have the same point of intersection, and that corresponds to dividing the equation by 20.
Okay, so I'm Anna again, after David and Montserrat details on the activities in the program. I'll talk now about the evaluations we did over 2 studies. The first one was developed with the first 3 cohorts of teachers in 9 school districts, and the second one in a single district. And it was a more recent one from 2015 to 2016. Okay, the first study showed that teachers in their classrooms that were observed by external evaluators and by our own research team were using much more multiple representations for functions while they were teaching topics, usually in the K-12 curriculum. They were addressing student reasoning much more often than at the start of the program. They were analyzing problems from multiple perspectives, and they were connecting math to real-world phenomena. And that was something happening as they took course 1, course 2, and course 3. The observation of the students' activities during the lessons showed an increased participation of students in lessons, the use of multiple representations, solutions to more complex problems, and explanations of ideas and strategies. When the courses were first offered in the spring of 2011, the proficiency of mathematics, according to the MCAS results, were below the levels for the state, but very close to those of similar districts. I repeat that. When the courses were first offered to teachers, the proficiency of mathematics, according to the MCAS, in Massachusetts districts was below the levels for the state, but very close to those of similar districts. 3 years later, the Poincaré districts had narrowed the differences from the state and had surpassed the similar districts by 5.1 percentage points. And most important, the greater the percentage of participating teachers for each grade in each district was related to the relative gains of the target district. and this was a significant correlation. In the second study from 2015 to 16, in one single district, we had 18% of Black students and 44% of historic students. We enrolled 53 out of the 83 elementary, middle, and high school teachers, and also 10 out of 21 other professions like special educators, coaches, coordinators, etc. PreK results before and after. The first two courses taken by the teachers in this district, we collected PreK results before and after the first two courses taken by the teachers in the district. The target district was then comparing two districts with similar previous results in PreK and also similar population in terms of ethnicity, income, English as second language, etc. This graph shows our results. It was very impressive that the target district actually improved 3 or 4 times more than the scores in the PreK scores in the target districts improved 3 times or 4 times more than the improvement that was found in the comparison districts or in the state districts. And also, Hispanic students did better, improved more than white students in the target district, and also the Black students slightly more than the white students. The reverse was true for the comparison in the state districts where, in fact, the improvement was higher for the white and than for the Black and Hispanic students. The data I showed before was in terms of percentage of students meeting or exceeding expectations, but we also got data on changes in mean performance level. And we have similar graphs. Much better results for the target districts, and especially for the Hispanic group, more improvement than the white students in the target districts, and white students improving more than the other groups in the comparison in the state districts. In summary, our results support the conclusion that the Poincaré Institute Teacher Development Program contribute to reduce differences between minority students and white students in state-mandated tests. Possible factors contributing to the results are, in our opinion, the interconnection and depth of topics afforded by a functions approach, the integration of math content and pedagogy, the focus on concepts and understanding, teachers' interactions with their peers and with instructors, allowing constant feedback, the classroom implementation of ideas from the courses, institutional and financial support, and teachers' commitment to work 10 to 12 hours per week on program activities. Teachers explored mathematics in more depth, and with this, they found new ways of introducing curriculum topics, taking student reasoning into account. Their confidence in students' capabilities may have grown after analyzing classroom research videos showing grades 3 to 5 minority students learning about variables, algebra, and functions. Black and Hispanic students' mathematical ideas were valued and was used as a basis for new learning. As such, they became confident in their ability to participate in discussions. Our results point to the importance of long-term and intensive teacher development programs that integrates mathematics content and teaching through the lens of functions. The program has been offered to in-service teachers, and we believe that incorporating our approach into pre-service teachers seems a relevant future goal if we want to make a real difference in mathematics education.
Hello. I do not see that many questions from the audience, but maybe a question that comes up often is whether the improvement in the state-mandated test came from the fact that we were teaching to the test, but actually we were not teaching to the test. So it happened by presumably a deeper understanding of mathematics seems to affect also the performance of students in tests, even if you are not teaching to the test itself.
I had submitted a question myself. In a way, it was triggered by the presentation, the keynote presentation we had before by Steve Leywand. And my own question was, what really made our students do better? The students in our target districts do better than the other students, and especially the Hispanic kids and the Black students, which somehow inverted the order that always shows white students doing better than the minority students for our target districts, while the similar districts remain with the same trend. There is so much in the program that's very hard to say that one of the factors is what led to those improvements. Actually, I do believe that it is the huge effort of having such a long period of time, 2 semesters, 3 semesters, with work with teachers for a deeper understanding of mathematics, working with them to understand the pedagogical aspects of teaching, which were, because of the approach we had, the functions approach, very much easy to be intertwined. The functions approach allowed us to open, to raise open questions, to consider different answers by the students, to involve them in discussions, while the teachers were well prepared to deal with those different aspects and different solutions.
Okay, so thank you very much for listening. And we hope to be able to talk to you again in the future and receive your questions.